Hey, welcome to the introductory course on correlation and regression. I thought I'd start just by showing you an example here and seeing where you guys are at the beginning of this unit. Take a look at this graph and tell me which of the following statements best describes the data in the graph above. I guess I should have changed that. I will let you pause, figure that out, and then come back and we'll talk about it. Okay, hopefully you've come up with an answer. In a study, recent study, 63% of American adults could read this and come up with the correct answer, and the correct answer is C. The more sugar people eat, the more likely they are to get cavities. Okay, so that's a pretty interesting finding because by the end of this unit, you should be able to read that very clearly, although right now, probably 20 of you were able to get that right, unless they're starting to teach this better in high schools. This is from 2014, so it's not like it was yesterday, but it's pretty recent. All right, well, this is an example of correlation and correlational research, and I'll use that as an example later on. So this is the introductory class. All I want to do here is sort of introduce what the concept of correlation is and what regression does in correlation. And to do that, I want to kind of help you shift your thinking from what we've been doing to this new way of thinking. It's a little bit different than ANOVA and t-tests. Just as a basic introduction, we need to look at graphs like the one you saw on that previous slide. Those are called scatter plots. And then 3 elements of correlation that we need to think about in order to analyze them. So we're not calculating anything right now. We're just going to kind of get used to the ideas. All right, so as I said, we got to shift the way we're thinking about things. When we did the z-tests and t-tests in ANOVA, we were comparing means. The inferences we made were about the differences between groups, inferences about differences. So if we go back to that original example with sugar consumption, an example of questions that would be answered by t-tests or ANOVAs would be, do some countries eat more than others? There you can divide things up into groups. So there's a group of maybe North American countries and a group of European countries. And you could do a t-test and say North American countries eat more sugar than European or something like that. You could also say, do some countries have higher rates of cavities than others? Again, you can identify specific countries and calculate the average in a certain part of the world and compare it to the average in another part of the world. So again, 10 European countries and maybe 10 African countries. Those are looking for differences and they're based on means. So correlation and regression was introducing a new type of analysis. And here what we're looking at is association. And here we're not averaging the same quality in 2 different conditions. What we're doing is we're measuring a bunch of examples. And we want to see if our variables tend to happen at the same time, or do they tend to happen at opposite times, separate times. And that is what we call an association or correlation. And that's what we saw in that first example. What we saw is that the more sugar that was consumed in a country, the more likely that country was to have cavities. So we're not averaging things and making direct comparisons. We're looking for a trend where sugar consumption and cavities happen together. Okay, so let's go back to that. What we're looking at specifically with correlation and regression would be very, very similar to what we learned about in the first couple chapters when we talked about descriptive statistics. So as you know, or I hope you remember this, descriptive statistics come in pairs. Normally distributed variables are best described by a mean and a standard deviation. Well, the difference in correlation here is we've actually got two variables and we're wanting to see if they go together. So this idea of central tendency and variation is going to look a little bit different. So imagine that line right there. That line is something that you calculated probably in 8th grade. I think everybody remembers taking graph paper to school and doing the slope of the line and the y-intercept. That's exactly what that line is. And in statistics, it's called the least squares regression line. I'll tell you about that in another video. But here, what you see is that this line could just go on forever. What this line represents is a measure of central tendency, kind of like the mean. And the way I want you to think about that is this is average sugar consumption. If it's around 20, on average, the number of decayed teeth is about 1. And you can see that on average, the number of decayed teeth goes up as the sugar consumption goes up. And so that regression line is really telling us, kind of like the mean, it's on average, that's where the value of the y variable is, tooth decay, when you're at a certain level of X, sugar consumption. The other side of this is this guy right here is an individual dot. If I back up, see there's a dot there, so I'm selecting that dot. That dot is an individual country, and notice that here is the regression line. So at 120 grams of sugar, there's a country and there's the regression line. So this right here shows that the particular country that we plotted has higher than average tooth decay. I'm just going to extract this thing right here. That thing is called a residual. It's kind of like a deviation. That's just showing the distance between an observed value and what it was predicted to be. Okay, so that amount right there is what we're looking at with residuals. So let's go back to this graph here. I showed you earlier that this thing here is a least squares line. It's a measure of central tendency. Well, look at this. If we look at all of the residuals, I've only done 5, but you should be able to imagine that every single dot on there has a residual like that. What correlation does is it measures variability. So the higher the residuals, the lower the correlation. Or the higher the correlation, the lower the residuals. The correlation then is a measure of variability, and a high correlation means low variability. It's an inverse relationship, and the reason for that is if you want to think about the central tendency here as a predictor, like if your regression line is making a prediction, a high correlation means it makes good predictions. It has lower variability. So that's a quick introduction to what a scatter plot looks like and what a regression line is, and the fact that correlation means that these residuals are small. High correlation means the dots are close to the line. All right, so I want you to look at a variety of scatter plots here. These scatter plots, they don't represent any real data. They're just something I found online and pasted them in here. But I want you to notice 3 things about these scatter plots. They have names. The first is the direction. And if you look here, you see that there's a positive correlation, and this is a perfect positive correlation. What positive means is that as the x variable here gets bigger, the y variable gets bigger. Over here, we have a perfectly negative correlation. X gets bigger, y gets smaller. So that's called positive or negative because in calculating them, you actually have to multiply 2 things. And if you know, if you remember, multiplying a positive value times a negative value gives you a negative number. So that's literally where the term comes from. So positive means they increase together, like sugar consumption and tooth decay. Negative correlation means they happen separately. That might be something like Oh, I should have thought of examples beforehand. Toothbrushing and flossing and tooth decay. So what you'll see is that most variables correlate somewhere in here, a zero correlation, and that just is called like a shotgun or a splatter, where there doesn't seem to be a trend, but sloping upward to the right is positive, sloping downward to the right is negative. Okay, the strength of the correlation is basically saying how well do the dots fit on that regression line. And as closer it gets to a magnitude of 1, the absolute value of 1, the stronger the correlation is. It's also called magnitude. Here, what you see is we have a perfect positive correlation of 1. That means if you calculated the formula for a line, it would hit every single one of those dots. Here, a straight line would hit most of the dots, so it's a pretty good correlation of 0.9. Even 0.5 is pretty strong. You can still see where a line would go through there, and it may not hit any of the dots, but the dots are going to be fairly close, whereas here, there's no angled line whatsoever. So that's zero correlation. So you move back to this way, you see once again you've got a perfect correlation. That's a correlation with a magnitude of 1, but it's a negative 1 because it's pointing that way. Okay, so strength, we like to see them closer to 1. Finally, linearity is important. Linearity means that the dots actually fit a straight pattern. You probably remember from Algebra 1 or Algebra 2 that you can do plots like this with polynomials and they curve. We're not going to look at that technique here. We're only working with linear regression. So we're going to work with situations where the lines are hopefully going to be straight. And even though those aren't perfectly on the line, I think you can still see that there's sort of a line or a linear trend in this one right here. All right. One of the fun things there is to do is to try to guess correlations. And so I'm going to recommend that you go to this site at some point and try to guess some correlations. We might do that in just a minute. But I wanted to give you an idea of some other correlations and how strong they are. We'll look at a few more examples. But what I did is I got a spreadsheet that has all of my department's graduates from the past decade, and for 340 of them, we actually have data about their GRE scores. That's the graduate record exam. It's kind of like the ACT for graduate schools. We also have their ACT test they took in high school, and we have their psych GPAs and overall GPA. So I correlated for those 340 students their ACT score from high school and their overall GPA at Augustana. Notice that's a 0.47 correlation. So we can tell something about a student's ability to do well at Augustana based on the ACT score. Psych GPA and the GRE. So our majors, if I calculate their GPA in the psychology major, so it's not neuroscience majors, just psych majors, and predict their GRE score, it's a 0.34. So those two things are correlated as well. Excuse me. Finally, the GRE is broken down into quantitative and verbal. And those two things correlate at 0.88. So if I know how well a student does on their quantitative, I know with pretty good certainty how well they did on their verbal. I'm not going to make a perfect prediction, but those two things are very highly correlated. So those are just some examples. Those are all positively correlated examples because these are all measures of academic ability and performance, right? So we would expect them all to be positively correlated. I would suspect that something like substance abuse would be over here, where the more substance abuse there is, the lower the GRE. The more time spent on video games may or may not be related to that. I don't know. Anyway, that's how those three things play out, and we'll look at some more examples later on. Okay, Want to talk about a couple last things here. One is that when people look at correlations, there's usually a sense, this is a psychological thing, where you try to find the connection. And that can be really misleading at times. So if you look at this, this shows, it's not a scatter plot, but it shows a correlation that there is a very high correlation between iPhone sales and the number of deaths caused by falling down stairs in the United States. Now, the first thing that I thought when I read this was like, that's because a bunch of idiots are looking at their iPhones going down the stairs, something that I've nearly killed myself doing a few times. Now, the reason that happens is because when you see those two things going together, it's pretty easy to come up with an explanation for why those two might be related. Now, it doesn't mean that they have anything to do with each other. It's possible that things are very highly correlated while having no real relationship. Here's another interesting one. Again, this is not a scatter plot, but it shows two things changing over time. And what you see here is that in the past, well, over a 10-year period, autism diagnoses almost tripled, and the organic food sales almost quadrupled. So they increased very highly at a certain period of time. And if you remember, the correlation, highest possible correlation is 1.0. That's 0.997. So that's an extraordinarily high correlation. Did anybody look at that and automatically think, oh, organic food must cause autism? I didn't have that reaction at all. But there are situations, had that been, of course, something like vaccination rates, there'd be a large chunk of people who would see that and go, oh, vaccination and autism. That's something we've all heard about, even though that is a spurious correlation. So in this case, I think that it's fairly easy to resist the impulse of thinking that there's some bigger connection there. So correlation really just means the two things happen together. So in fact, there is a guy, I believe at Harvard, Tyler Vigen, who has some great spurious correlations that show you things that you would not expect to be correlated are correlated. One interesting thing that's correlated, this is actually a correlation between, I'm going to have to, here we go. There we go. So that's a correlation between the chocolate consumption per capita and the number of Nobel Prizes per 10 million people in the population. So here we have a clear correlation that the more chocolate consumption there is in a country, the more likely they are to win the Nobel Prize. All right, so does that mean you need to eat chocolate? Probably not. In fact, it's probably more important to know that the Nobel Prize was developed by a Swedish man and administered by the Swedish committees, and the countries that win a lot of prizes are culturally quite similar to Sweden, whereas other places who have a lot of high-tech stuff may not be as similar. So I don't know. Maybe the correlation is spurious. All right, to summarize, what we've done here is I've shown you that regression is type of central tendency. It's kind of like an average moves. As the x changes, the average value of y can change too. The correlation coefficient measures variance, but it's like the opposite of variance. So high correlation means low variance. And instead of the variance around the mean, it's variance around the regression line. Okay. So we have central tendency and variability there. The type of line, as I mentioned in that one slide, is it's called a least squares regression line. I'm going to have to illustrate that in another video. So I think what I'll do is next time, I'm going to show you how to do the hypothesis test for correlation, and then we can do a little bit of exploration about how to interpret it and how to think about predictions.